All right, so let's look at flow for nozzles and diffusers. And we want to look right now at the shapes that these things could have. And essentially our choices are going to be, it's either going to be converging, means it gets smaller, or diverging means it gets larger, or converging, diverging, where it does sort of both. So we have some equations. I'm not going to derive these, but it's derived in your textbook, and you can look at that if you're interested. It's pretty much just continuing the derivations that we had done in the previous sections. So the relationship between velocity and pressure is that change in pressure divided by density is equal to the negative change in velocity times change in velocity. The important thing here is that as the velocity increases, so if dv is positive, then since I'm multiplying by something negative, I'm going to have dp, the change in pressure, decreasing. Conversely, if this is decreasing, so less than 0, this has to be positive, and so therefore will increase. If I look at the relationship between velocity and area, okay, so like the pipe size area that it's flowing through, I end up with this expression, which is more complicated, but basically I have change in area divided by area is the negative change in velocity divided by velocity times 1 minus the Mach number squared. And so when I look at this one, I'm going to have to consider how the Mach number changes as well as how the velocity changes. So there are 4 cases that we will look at. So first we'll look at a subsonic nozzle. So a nozzle, my purpose is that I'm trying to increase the velocity. If I start out with a Mach number being less than 1, okay, so it's subsonic, then 1 minus m squared is going to be positive. And since I'm trying to design a nozzle, the velocity will increase. And so if I look at this equation, that says that the area has to decrease. So the duct is going to converge. It's going to be designed sort of like this. Also, if I look at this, the other equation tells me that that means the pressure will also decrease. And so for a subsonic nozzle, the velocity is going to increase. That's the job of the nozzle. The way I'm going to do it is through building an area that's decreasing, and that's going to mean that the pressure will also decrease. If I want to look at a subsonic diffuser, still looking at m less than 1, 1 minus m squared is positive. So now a diffuser's job is to decrease the velocity. So this will be negative times something positive times this negative means dA will be positive. The area will increase. So to build a subsonic diffuser, I want the area to increase. As I do this, I'll also find that the pressure will increase going through this change in duct area. Now what about supersonic? Okay, so now then the Mach number is going to be greater than 1. 1 minus m squared will be negative. So negative, negative. If I increase the velocity as I would in a nozzle, that means that the change in area has to increase. So it is counterintuitive, but I'm actually going to, a nozzle for supersonic flow will increase in area, but the pressure will still decrease. So the duct is going to diverge, but because the flow is supersonic, this is going to actually increase the velocity. If I want a supersonic diffuser, therefore, I'm going to have the opposite effect. The area is going to decrease, so supersonic flow through something where the area decreases will actually decrease the velocity. But the pressure will increase just like as it did for the subsonic case. Now where this gets interesting is if you put a converging and a diverging unit one after the other. Now let's consider the case of subsonic flow. So m is less than 1. And so, my first thought is, and maybe this is true, if m is much less than 1, the velocity is going to increase going through this nozzle. But if it continues to be less than 1, then when it hits this narrowest point and then moves into the diffuser section, the velocity increased, but now the velocity will decrease. Okay? The net effect is what we're calling a Joule-Thomson valve in many cases, sized so that the increase and decrease counterbalance each other. That's interesting, but what if, as the velocity increases, I reach the point that it becomes sonic? So let's just say, for the sake of argument, that right here at this narrowing, the Mach number is 1. So it's subsonic, it's increasing, and it just barely reaches the point of being sonic. Okay? Slightly over 1.001. It is now supersonic. What will happen as it goes through this diffuser? So most of you probably got this right. Yeah, the velocity is going to increase, so it's increasing along here. I get to m equal to 1, and now then it's going to continue increasing. So going through a convergent divergent nozzle, when I'm in that transonic area, when the Mach number is very near 1, if it gets to 1 at the throat, the smallest area here, then it will continue to increase in velocity as it moves through. Now I can also have started with something where it was supersonic coming in, and in that case, if I build it in this direction, I will have it diffusing, right? The velocity will slow down if it comes in as supersonic. And if I can choose correctly so that I get m equal to 1 right here at this narrow opening, and then put a diverging piece here, it's now subsonic and will continue to decrease the velocity. So at this point, I'm going to break the video. I'm going to come back and look at what's going to happen when we do back pressure with these various styles of nozzles or diffusers.